Good morning and yes, good evening, guys outside. Are you guys seeing my screen and hearing me? Is there a problem with the sound?
Sound is not activated.
Are you able to hear me now? Okay. Let me see. All right. So as I was saying, there is a request from some people with COMSOL issues, and so I don't want you to give up. You learn more by actually doing it. And so I'm trying to encourage that. So I'm really very flexible with time. I will extend it again by 2 more days. In fact, one time I thought of making all the assignments due on the last day of classes. I've done that in the past. But time management would be a problem for you guys, because if I put that in, then you also delay, and then all of a sudden you have a project due and assignments due. So
a bunch of questions about the last week. A bunch of questions last week.
Last week, right. So, well, you are graduate students. You should have some responsibility of spreading the time around. Okay, so let's begin. So we are entering into the next phase of the course where we are going to look at solving differential equations. So we are setting it up maybe in a lecture or two, covering basic ideas in functional approximation, and then we will move on to ordinary differential equations and initial value problems, boundary value problems, some of the algorithms, ideas that are used, concepts of stability, numerical stability, and sources of truncation errors. How do we control that with grid distribution? These are some of the ideas that you should carry if you're going to use COMSOL, Fluent, etc. in an intelligent fashion. So we will use simple examples to go through what the concept is so that you understand. So in the last class we reviewed essentially curve fitting exercise. So if you're given a set of data points, how do I fit a curve? And that problem essentially reduces to a problem of solving a set of linear algebraic equations. So if you have the number of data points and the degree of the polynomial, in the case of polynomial curve fitting matching, then you make the curve pass through every one of the data points. So you make the residual at those data points equal to 0. And that is the idea behind collocation method in differential equations later on. And if you have more data points and you're fitting a lower degree polynomial, then you end up with a least squares approximation, where you cannot make the curve pass through any one of the data points, but you can minimize the error between the predicted value from the equation you are fitting and the experimental value that is given to you. The same ideas can be applied for representing other functions instead of having data from an experimental point. But in each of those cases, we had to reduce the problem to a problem of solving for the coefficients, the unknown coefficients in the polynomial, into a system of linear algebraic equations. And we saw that in some cases it leads to very poor scaling if you go for very high degree polynomial with the polynomial functions, the basis functions being 1, x squared, x cubed, etc. So there are other ways of choosing these basis functions that yield better scaled matrices. But today I'm going to talk about what are called difference operators, and this sets the stage for finite difference approximation for solving differential equations of all kinds. And so we're going to look at a problem where we have a given set of data points, xi, fi, and the points are uniformly spaced in the independent variable. So xi at any location can be calculated if you know what I is, the grid point location. Okay? So the picture to keep in mind is if I have some range going from A to B in the variable x, I'm going to put a set of grid points on that are uniformly spaced. Okay? And I'm going to label them as x1, x2, all the way up to whatever xn I have in data points. So they are calculated basically from this equation. So h is the step size, the interval between these 2 points. Okay, that will be called h. And I is the index that we are going to use for any grid point. So when I is equal to 1, for example, you get x1, I equal to 2, you get x2, etc. Okay, so yeah, as I said, this is the difference. So we need for this method to work, and this method avoids having to solve a system of algebraic equations. It has a lot of advantages. It is recursive in nature, and it's very easy to evaluate the coefficients of the polynomial without solving a set of data points. But you always make every data point pass through the curve. Okay? So it's called the Newton polynomials, and that's what we are going to develop. And they form the basis for not only functional approximations, polynomial curve fitting, but also for developing algorithms for ordinary differential equations, and the finite difference approximations for boundary value problems and partial differential equations. You might have seen this, so it may be kind of a repetition for some of you. Have you seen the finite difference operators? Okay, so here we are defining a forward difference operator. Okay, so this is a definition. Okay, definition of a forward difference operator defined as delta fi. So delta is the operator operating on fi, and that is defined as fi plus 1 minus fi. It is called forward because it uses the point ahead and the current point. Similarly, we have a backward difference operator, and it is indicated with the delta operator like this, the opposite of the previous one. And this is defined as fi minus 1. So it takes the current point and the point behind that. Okay? And you can then define something called, these are all just definitions, a central difference operator indicated by delta, but it takes points on either side of the reference point. Remember, we are dealing with a set of tabulated data points, xi, fi. So I have a table like this. Okay, and I will have numbers here. Okay, so I'm taking differences of points that are equally spaced. Now here we are indicating as half, but it could be 1 or 2 or whatever. That will determine what your step size is. Okay? And then we have a shift operator, which we define as EFI, which simply returns the value of the next value. Okay? So these are all rules, just like derivative is a rule. What is derivative after all? We indicate it as df, or the derivative of f with respect to x. So there is a definition in the limit process, and there is a recipe for calculating what the derivative is. So in the same way, you have to think of all these operators as definition and the recipe that goes with it that allows you to calculate what those differences are. And there are relationships between them, obviously. Okay? And using these relationships, to me, when I learned this first, it's as if it was magic. I can develop a whole series of polynomial functions accepting this definition and using some very simple concepts from algebra. So if I have this definition of a first derivative that you see here, I can then apply that twice. Okay? That is, a first derivative operated on another delta. So just like I have a second derivative from here, I could have a second difference. So the second difference would be difference of the first differences. So I expand the inner part first. Delta fi by definition is fi plus 1 minus fi. Then I operate the delta on each one of them. Okay? And so now delta fi plus 1, according to the definition, will be fi plus 2 minus fi plus 1. And similarly, delta fi will be fi plus 1 minus fi. I can combine those two and write it as fi plus 2 minus 2 fi plus 1 plus fi. I think there's something missing there. Okay? You should have a plus fi. Okay, so now we are going to see whether we can discover relationships between these operators that we have defined. So the first thing is to generalize this. You can now define third difference, fourth difference, etc. And in Matlab, the function that gives you all this is called DIFF. If you look it up, it will allow you to calculate. I think with these vibrations, the screen is losing the resolution. So you can calculate the first difference, second difference, third difference from a table of data points using these formulas with that function DIFF in Matlab. Okay? So EFI by definition is defined as fi plus 1. delta fi by definition is defined as fi plus 1 minus fi. Okay? So what if I take this fi plus 1 and replace it with e of fi here? Okay? So then I'm trying to now discover the equivalent relationships between the various operators. So delta fi is equal to e of fi minus fi. Okay? So fi is the common thing, so I can take this out and write it as e minus 1 operated on fi. Okay? So what this tells me is that when I have some operator delta operating on some variable fi, I will get the same result as if I operate on e minus 1 on the same value. Okay? So these two operators are equivalent. Delta is equal to e minus 1. They produce the same effect when I operate them on any quantity. This is called operator algebra. So I'm looking at algebraic relationships between operators. Okay? So if they operate on certain quantity, both sides will produce the same result. Okay, now you can rearrange that as e equals 1 plus delta, as I've done there. Okay, and I can apply these operations repeatedly, right? That is, this is the first time. If I apply it the second time or a third time, the result will be the same. So I'm going to take e to the power alpha, and that will produce the same result as 1 plus delta to the power alpha. Okay, operating it alpha times. Okay. Now I say, okay, now what does it operate on? I'm saying I'm going to identify that as it is operating on f of x. So what is the meaning of e to the power alpha operating on f of x? The meaning is it is f evaluated at x plus alpha h. Right? If alpha is 1, I'm displacing it by 1. If alpha is 2, I'm displacing it by 2. What happens if alpha is 1.5? Displacing it by 1.5, right? So we're letting alpha be any number, integers or any real number. Okay, that's one of the generalizations, and that immediately gives you a very powerful result. Okay, so and what is that result? Here I have e to the power alpha operating on f is the same as 1 plus delta to the power alpha operating on f. Okay. So we are dealing with a set of data points that are equally spaced, and here we cannot do least squares in this approach. Okay, so we need to have the degree of the polynomial being determined by how many data points that we have. So if we have m data points, I'm going to fit a polynomial of degree m minus 1, and the polynomial will pass through all the data points. Okay, and so the function can be any arbitrary function. The data, either it is given in the form of a tabular data. We are saying that if you try to fit it through a polynomial of a certain degree, it will not be an exact representation of the data or the function, because it's an approximation that we are building. So there will be a residue. Okay, and the left-hand side of this one we already saw gives us e to the power alpha f of x gives us f of x evaluated at x plus alpha h. That is the meaning of e to the power alpha. It's shifted alpha times, okay, in units of h. On the right hand side, I'm going to do a binomial expansion of this term, but it is operating on the same f of x. Both on the left and on the right, it's operating on the same f of x. So when I do the binomial expansion, I get this term 1 plus alpha delta plus alpha times alpha minus 1 over 2 delta squared, etc. It just goes on forever. It's an infinite series if alpha is not an integer. But if alpha is an integer, it will have a finite number of terms. Okay. For example, if alpha is 2, you expand it, it's 1 plus delta squared plus 2 delta, right? So, but if it is not an integer, then you will have an infinite series. But it is all operating on f of x, okay, on the right hand side. And that is your representation for the polynomial. So the magic is here, really. Because if you give me a set of tabular data points, I can construct and evaluate each one of these delta, delta squared, delta cube, etc., operating on f of x. So alpha becomes my variable. So I have done effectively a coordinate transformation from x to alpha. Okay, so I need to pick a reference point x1, and from there I measure in units of h with alpha as the independent variable instead of x being the independent variable. So this is a polynomial in alpha. You will see alpha, alpha square, alpha cube term appearing. But these delta operator on f, delta square operator on f will all be just numbers. So I don't have to solve for a linear system. I just pull these numbers because I can calculate them. I know what the definitions are for delta, delta square, delta cube, etc. Okay. So now I have to decide when I want to truncate this. I can truncate it in one term, truncate it in two terms, three terms, etc. Then I'll get a linear polynomial, quadratic polynomial, or a cubic polynomial. Okay. So these are called the Newton forward formulas. They are called forward formulas because they depend on the definition of a forward difference approximation. And they use points ahead of time, ahead of that particular reference point. Similarly, you can discover a relationship between E and the backward difference operator, and I'll show you how that looks. So you have a whole class of Newton backward polynomials. Okay. Any questions so far? Simple stuff, right? So I talked about the coordinate transformation. Here it is. Okay. So x is the original variable, x1 is the reference point, h is the step size, unit of measure from one grid point to another point. So I've made the coordinate transformation from x to alpha. Okay. So I'm getting a new polynomial in alpha, and alpha can be 0, 1, 2, say up to m minus 1. So I'm truncating it. If you give me m data points, the highest polynomial that I can construct is only of degree m minus 1. Okay, so I'm going to split that expansion into two parts. Okay, so you see it here. Okay, this is my transformed variable. So alpha are my unknowns now. Okay, wherever that appears, and you see that when I say recursive, what I mean by that is if you have three data points and you fit a quadratic, and then another data point comes from online, for example, and you want to build the polynomial of a next degree, you don't need to recompute any of them. You just need to add one more data point and compute the next highest difference coefficient, and you have a higher degree polynomial. But since we are truncating at m minus 1, because we have only m data points, the polynomial is of degree m minus 1, we have a residual. Let me ask you to see whether you understand what we are talking about. What would be the residual value when I calculate this function at alpha equal to 1, 2, 3, 4, etc.? The question is, what will be the residual, what would it amount to, what it would calculate to, if I calculate this polynomial at values of alpha equal to 1, 0, 1, 2, etc. They will all be zeros, okay? Because the function passes through those data points. There is no residual, okay? What is it?
Give us some message.
Message, some questions? Yes, you are right. Thank you. It will all be zero, okay? The residual at those data points. But if you calculate alpha at any other location, you can see it, okay? So what is the residual? Terms that are left behind, right? Suppose I'm constructing a second degree polynomial, so I'm truncating it here, okay? Then this is what I would call as the residual, the next ignored term. Put alpha equal to 0, knocks it down. This term. Put alpha equal to 1, that term knocks it down. Put alpha equal to 2, that knocks it down, right? And so the residual will be exactly 0 at those locations. That's what tells us that this polynomial passes through all the data points that are given. Okay? But if you evaluate them at any other alpha, those terms will not be 0. Okay? There will be an error. That's what gives you an interpolation polynomial with an interpolation error. Okay? How do I construct this polynomial coefficients? So this is how I do it. So there you see the polynomial of a certain degree m minus 1 with m minus 1 terms, and so the next neglected term is going to be of order h to the power m in the polynomial. Okay, and if you give me these data points from an experiment, x and the corresponding f, I construct this difference table. And it is very easy to do. This is where you can use DIFF in Matlab to help you construct the difference table. Okay, so it will take the order of the difference as an input parameter and the table of data. It doesn't care about X because it assumes data are equally spaced. Okay, so you give it F and you give it the degree of the difference, which identifies which column you want to calculate, and it will do the calculations for you and return that. So the number of entries that it returns will be less than the number of entries that you put in by the order. Okay? So the first difference, delta F1, is calculated simply as F2 minus F1. So you're using these data points. Okay? And similarly, if you're calculating delta F4, you are using F by minus F4 because it's a forward difference. Now you can think of it as delta F4 being a forward difference for F4 or a backward difference for F5, right? So when we look at the backward difference table, it will have the same numbers, it will look the same, just a matter of interpretation. Okay? So once you construct all these numbers, all you have to do is go back and, okay, I need delta of F1, here it is. If I choose this as a reference point. But if I choose this as a reference point, then I will pick the number that comes from here. Okay? And if I want to increase the degree of the polynomial, I need delta square operating on F1. Oops. Okay? Here. So that means that is this number, if my reference point is there. So you need to identify where your reference point is. That determines which row you're going to pick the numbers from. If it is X1, those are all the numbers that you will pick and then plug it in. And you have a polynomial representation for that data point without ever solving for a system of linear equations. And when I say recursive, what it means is if you did it for two data points, and for example, in delta square F1, what are the data points that will be involved in calculating that? X1, X2, and X3. But if I have one more data point, X4, then I will be able to calculate delta Q F1 as an addition. Then I can just increase the term, the next term in the series, and increase the degree of the polynomial. Any questions? Okay. These are simple stuff, easy stuff, right? Here is just an example of that idea. So I have a set of tabular data, X, and equally spaced, 2, 3, 4, 5, 6. So what is H here? 1. Okay. And I have a set of function values. By inspection, you can see where these functions are coming from. Where are they coming from? X cubed, right? And then I construct the difference table. And because the original function that provided this data is coming from X cubed, what do you notice about delta to the power 4? What is the derivative of X cubed? The fourth derivative of X cubed will be 0, right? You see the same thing reflected here. Now, how would I construct a first degree polynomial using 2 as a reference point with 8 as 1? Okay, so I have only 2 plus alpha. Well, I need to take the first coefficient, 8, and then the second coefficient, 19 times alpha, and that's it. Okay, that's a linear polynomial that will go through these 2 points. If I ask you for a quadratic, what will that be? Just left it open. Around the same reference point, what will you write that? 8 plus alpha times 19 plus alpha times alpha minus 1 over 2 factorial. It's not alpha squared. Remember, that formula is still the what you have to deal with, times the delta square, which is 18. I think you get the idea, so you can write the next one. And I said verify P3 passes through those 3 data points. Here, you can verify that P2 passes through those 3 data points. Okay, what would happen when I put alpha equal to 0? I get 8. When I put alpha equal to 1, 8 plus 19, which is 27. Right? When I put alpha equal to 2, you need to do a little bit of arithmetic, and you will find that it comes out to 64 as well. Okay. Then I said, as a simple exercise, calculate a second degree polynomial with a different reference point, 4. Okay. So what would that look like? Now 4 is the reference point. So I'm going to take all the points that I have highlighted here. So if it's a second degree polynomial, it's going to be 64 plus alpha times 61 plus alpha times alpha minus 1 over 2 factorial times 30. Okay, that will be the reference point here. Oops. Now, backward difference formula. So that gives you a whole class of higher, progressively higher degree polynomial. That's going to be the basis for taking derivatives, numerical derivatives, because now I have a polynomial representation of a set of data. So if I'm interested in calculating the derivative of that data, suppose, let me just talk about this idea so that you understand. Suppose I have equally spaced data that is given to me, and I fit a polynomial. So I have a polynomial representation. But I'm asked to calculate what is the derivative of that function at a particular point. The first derivative, the second derivative, etc. So I have a functional representation now of the data. So I can go and take the derivative of this with respect to what? Alpha, right? With respect to alpha, and translate that into x. So I can do that for first derivative, second derivative, etc. Those give us the finite difference approximations for differential operators later on. And of course, when you take the derivative and evaluate it at that point, what would happen? Will the derivative contain any error? The function, when I evaluate the function that I fitted and evaluate it at these points, we just said that the function doesn't have any error because it passes through data points. Yeah, that's how we are constructed. So what would happen to the derivative? No, it will always have an error. And the error will get larger and larger as you go for the first and second derivative. You will have to understand when you see why that is so. Okay, I'm just sowing the seed right now, but the derivative is not 0. Okay, but you can also evaluate the derivative at any other location too, just like you can evaluate the function at any other location. But even if you evaluate the derivative at the same location as the data point, you will still have a certain error. I'm going to do that very soon today. Okay. Now, for the backward difference formula, do you understand where this comes from? It's again a discovery of relationship between the shift operator and the backward difference operator. Okay. Can you assume that everybody is okay with that if I give you that equation? So then what I'm doing is I'm doing exactly the same thing as I did for the forward difference operator. On the left hand side I expand this, and that gives me shifting in the forward direction. Okay. If I put minus alpha, then I will be shifting in the backward direction. Okay. But here it is plus alpha. And I have 1 minus the inverse, the backward difference operation, to the power minus alpha. Okay. So let's again do a binomial expansion on that. And that's going to give you 1 plus alpha delta plus alpha times alpha plus 1 this time, over 2 factorial delta square plus alpha times alpha plus 1 times alpha plus 2 divided by 3 factorial delta cube, etc. Okay. So once again, it's an infinite series if alpha is not an integer, and you need to truncate it, and that will give you a truncation error. Okay. So that is how you would use a backward difference operator. The same set of data points, our labeling has changed. Now I call this as my reference point, x0, y0. Okay, so all the points are labeled as -1, -2 because they are looking behind from the reference point. What this means now is, okay, I'm calling this as x0. So this will be x -1. This will be x -2. They're all behind in the ordered sequence. Okay, and we are going to calculate the differences using the backward operation, but this table is the same. Okay, it's just our reference point has shifted to this, and we are looking at these numbers as being the backward difference. Exactly, the numbers will be the same from the table that you have constructed. So we need to pull these numbers and putting it into the backward difference formula. and alpha would be 0, minus 1, minus 2, minus m from the reference point. You need to shift backwards, okay? And that's what will make all these things 0 as well. When you put alpha equal to minus 1, this term goes to 0. And when you put alpha equal to minus 2, that term goes to 0. So the backward polynomial will also pass through all the data points. Just our references from the current reference point, we're taking all the data points that are behind it. In forward difference, we're taking the points ahead of it. Oops. This is an important table because I'm using the same numbers but looking at two different interpretations. Okay? If you understand what we have talked about so far, I'm going to ask you a few questions and let's see whether we can answer those. Okay? Suppose I take minus 2 as my reference point, x at minus 2. That is, I'm taking x equal to 4 as the reference point. And I'm constructing a forward difference formula, a polynomial, a second degree polynomial. So what are the data points that I would use? Newton forward formula, so I will use all the data points along this line. Okay? So what will be the formula? You can write the formula. Maybe let's do that. It's going to be 1 plus alpha times 64 plus alpha times alpha minus 1 over 2 factorial times 61 plus alpha times alpha minus 1 times alpha minus 2 divided by 3 factorial times 30. Okay, that is a Newton forward, third degree forward formula. Third degree? What did I do wrong? I think I did something wrong. Can you guys identify what I did wrong? I wanted to fit only a second degree polynomial using the 3 data points. So the first one should be 64. Let me just erase that. Okay, so the first term should be, remember, maybe let me go back because I myself got confused. I want to make sure that you don't carry that confusion with you. Okay, when I do an expansion like this, the first term is 1 operating on f. So the first term itself is the function value. Okay, it's not just 1, but it is a function value. The second term is alpha times delta operating on f, that reference point. Okay, so that is the second term from that table. So that's where I made the mistake. So let's go back and write that formula. So this is a Newton forward formula I'm going to write with a reference point of 4, x equal to 4. Okay, and that's going to be 64 plus alpha times. Are you guys seeing what I'm writing on the board? Here itself is giving us problem because of this vibrating screen, I think. Maybe let me go to the computer and try to 64 plus alpha times 61 plus alpha times alpha minus 1 over 2 factorial times 30. Okay, that is a Newton forward formula taking these data points that we talked about, 64, 61, and 30. Okay. Now I'm saying now construct a Newton backward formula with the same reference point. Okay. So Newton backward formula. What will that be? 64 plus plus 1. Question to you is, I'm using the same reference point. I'm constructing a second degree polynomial. Are they the same polynomials? Meaning, if I put alpha equal to 1.5 in these two, am I going to get the same result? You would say no, but can you say why?
Because if you were to do an
take the third term and expand the alphas.
Yeah.
Expand it out. You'll get a polynomial in alpha squared, but your coefficients don't match up.
That's the exercise you need to go through to answer the question, are they the same polynomial? You need to expand the first one and the second one and see whether the coefficients of 1 alpha and alpha square are exactly the same. If they are exactly the same, then you have the same polynomial. Okay? And it turns out that they will not be the same, you are right. Okay? But you didn't do this by expanding it in your mind, right?
Yeah.
So is there any other reason why you would think that they should not be the same? There is a easier, better reason, and that is to say that the Newton forward polynomial uses 4, 5, and 6. Right? Newton backward polynomial at the same reference point uses 4, 3, and 2. Right? In calculating those coefficients. So they represent different data set. Okay? So if I use the Newton backward polynomial and calculate it at x equal to, at this point, interpolation, that would be a true interpolation because I'm using the data points in here. But if I use the Newton forward formula and calculate the value of x up there, that would be an extrapolation because I'm going outside of the data points that I have used to construct that. But if I construct a backward polynomial with this as a reference point, then what would happen? Those two polynomials would be exactly the same. The coefficients, when you go through the exercise that you talked about, expand all the alpha, compare the coefficients of 1 alpha and alpha square, you'll find that the polynomial that is coming from this as a reference point with forward and this as a reference point with backward will be the same. And the reason is they both use the same set of data points in building the polynomial. There's only one unique representation for a polynomial passing through a given set of data points. Okay, so it's easier to understand that way. I guess I have a few exercise problems here that you can work through. Numerical differentiation. How do I take derivatives of data? Okay, and the same idea will be used later on for solving differential equations. This will give us the so-called finite difference approximations for derivatives. So as I said earlier, the starting point is I have a function which is approximated by a polynomial that you see here. Okay, and I have an expansion for the polynomial with a truncated series. So I have certain error. Okay, so what I'm going to do is I'm going to take the derivative of this function with respect to x. That's what I want. What is df dx? Once you give me the data points, I calculate the polynomial, put it there, and I want to take the derivative of that. Okay, so df dx is written as using chain rule. First, I'm replacing the f with its polynomial approximation. So d dx is operating on the polynomial approximation of degree m minus 1. So this is an approximation because it contains a truncation error there. Okay? And then I'm applying the chain rule because the polynomial that I have constructed is a function of alpha, not x. So I just use the chain rule, the alpha of p multiplied by d alpha dx. But I know what d alpha dx is. How do I know that? Because I know that x is equal to some reference point plus alpha times h. So if I take dx d alpha, x1 is a constant here, h is a constant. So all I'm going to get is h, or d alpha dx is 1 over h. Okay, so that's what gives rise to the 1 over h term here. This d alpha dx is 1 over h. And then I go into the formula and take the derivative of every one of this formula. This now you will see why it is not going to be, the error is not going to be 0 exactly at every point. So if you go back to the function, do I have the function here? So what is the derivative of 1 operating on f? It doesn't contain any alpha, right? It's a number, so it's going to be 0. And in this series, what do I expect? I expect the leading terms to be larger in magnitude and the subsequent terms to be smaller and smaller in magnitude. Okay, that's the reason or the rationale why I say, okay, I'm going to truncate at a certain level because I expect the truncation error to be small. So I've lost the most valuable term in the polynomial approximation by taking the derivative. That's why the derivatives always have larger error than the function. Opposite will be true for integrals. We can use the same formula to develop trapezoidal rule, Simpson's rule, other quadratures, and you'll find that the error actually is smoothed out because of that. You can also understand it in terms of graphically. If you have small error in data points, it's going to be amplified when you take the derivative. It's going to be smoothed out when you take the integrals. And remember also I have a 1 over h term. So I must also divide this one by 1 over h. That will tell me that the order of the error is going to go down by 1 whenever you take the first derivative. Take the second derivative, it will go down by 2. Okay? So all I'm going to do is take the derivative of each one of these terms. So the first one is dropped. The second one is simply derivative of alpha with respect to alpha is 1. But the third term, you have to apply the chain rule. It is alpha times alpha minus 1. So it's going to be alpha plus alpha minus 1 when you take the derivative. Okay? So the first leading term is simply delta in the derivative, first derivative. And the second term, when you apply the chain rule on the product alpha times alpha minus 1, you will get alpha plus alpha minus 1 over 2 delta square. And on the third term, which was alpha times alpha minus 1 times alpha minus 2, when you apply the chain rule, you are going to get alpha times alpha minus 1 times the derivative of alpha minus 2, which will be 1, plus alpha minus 1 times alpha minus 2 times the derivative of alpha, which will be 1. So that's essentially the chain rule. Alpha times alpha minus 2 multiplied by the derivative of alpha minus 1. Okay? So and the order goes down by 1 more, as I said. Okay? So this is the formula that will give rise to a whole class of finite difference approximations for derivatives. What this tells you is, if you give me a table of data points, I can evaluate numerically what derivatives are by plugging into the formula that I get from this. And as an example, you take at a reference point x1, which is alpha equal to 0, okay, and m equal to 2. When you take the derivative, you're basically truncating it after this term. Okay, so what you'll get is 1 over h times delta operating on f of x1, because x1 is the reference point. That tells you you are calculating the derivative of the function. I guess I should call it an approximation to that at x1. Okay, because that's what determines where you are evaluating the derivative. But you're going to use the definition now of delta f1, which is f2 minus f1. Okay, and the important point is you get that the truncation error is of order h. So if you have the smaller h, that is points are closely spaced, you will get a better estimate of the derivative. Okay, but so this essentially is the forward difference, but now because it's a derivative, I need to know how far apart the data points are. Okay, and that's very easy to interpret geometrically. If you give me two data points, f1 and f2, and you ask me what is the slope of that, it's simply f2 minus f1 divided by the spacing. It is this distance divided by this distance. But the nice thing is I can now generalize it. I can say, okay, I want the first derivative to be more accurate. Well, one way would be to don't truncate it at 1, but truncate it at 2 terms. Okay, and that will have a truncation error of order h squared. Okay. Remember, the next neglected term is of order h cubed for the polynomial approximation, but it is of order h squared for the first derivative because we are dividing by h. So here is a 2-term expansion. And so I need to substitute alpha equal to 0. Why? In that formula that I have here, I'm substituting alpha equal to 0. Here I indicated that. Why? Because I'm calculating the derivative at x1. If I want to calculate the derivative at another location, for example at x2, I can put alpha equal to 1. Okay, so that's what gives you a whole class of approximations at different reference points. So when you substitute alpha equal to 0, this will drop out, this will drop out, you'll get minus 1 over 2 delta squared. Okay, and that's how you understand this term. Okay, delta minus delta squared over 2 operating on f of x1. If I had put alpha equal to 1, that I will be calculating the derivative at x2, but I will still be this will be operating on f of x1, okay, because that's what my reference point determines what that function is operating on. Where I am evaluating is determined by my alpha value. Where is the alpha value? Yeah, for the function. Okay. So it is again fairly easy to expand this, but I just need to expand delta square f1, and so here I've shown delta f1 is f2 minus f1, the first term, and delta square f1 is okay, here you have f3 minus 2f2 plus f1. That is, from f1 you are taking 2 points ahead to calculate the second difference, and then you simplify this and you'll get this formula. This is the formula for, it's called a 3-point difference, 3-point forward difference formula for the first derivative. So it is based on the reference point x1, but it takes 3 data points, f2 and f3, but it gives you an approximation for the first derivative, which is more accurate because it has a lower truncation error. Remember, h is normally less than 1. So you would say that h square should give you a more accurate result. Okay? Any questions? So we go through this process for the second derivative, third derivative, etc., and tabulate all the results. What am I trying to show here? Two-term expansion. Let me ask you, what am I trying to show here? It is a two-term expansion that we did. Yeah, you're on the right track. We just did a two-term expansion. It's the same thing. I'm going to truncate it at this location. Okay, and that's what you will see. Okay, I'm truncating at this location, but what am I putting for alpha value? 1. Okay, that means what am I where am I evaluating the derivative? At x2. Okay, my reference point now is still x1. My reference point is x1, but where I'm evaluating the derivative is at x2 because I have put alpha equal to 1 in this. Okay, otherwise it's the same as I did before, but I get a different formula. Okay, so what is the interpretation of this formula? So you do the expansion and simplify it, and you will get this formula. It's a very important formula, and it is called a central difference approximation for the first derivative. It has a truncation error of delta x squared. Okay, and we will use this a lot when you use finite difference method for solving differential equations. So it is allowing you to evaluate the derivative at the midpoint using points on either side. So it's f3 minus f1 over 2h. Essentially what it is doing, if you think about it, is if, pardon me, any question? It's averaging the 2 points. You can think of it like that. Yeah, right. But a more proper interpretation for that would be if you have 3 data points like this. Okay, you are calculating the derivative at the middle by putting a quadratic through that and asking what is the derivative at that point from a quadratic expression. Okay, and that's why the error goes down. So if you had a linear one, as in the first difference approximation, you just take either this point, which would be a backward difference approximation for the derivative at here, or you take these 2 points, which will be a forward difference approximation for the same point. But now this one gives you a central difference approximation. Both forward and backward will have an error of order h. This one has an error of order h squared. We don't really learn much more about the error than to say that it is of order h or h squared or h cube, etc. Okay? So the Taylor series expansion will tell us a little bit more, and we'll be able to understand why the grid, this tells us why the grid size controls the error. So in your project, for example, we want grid independent studies. What does it mean? We want to make sure that as you continuously refine your grid, that is, make h small, this becomes a better and better approximation for the derivative. That means your solution will become a better solution for the differential equation. Okay? But there is another term in the truncation error that we don't get to see from this polynomial expansion. And we will see when you do the Taylor series expansion method for deriving the same formula. Any questions? Now the second derivatives, same idea. Okay, so I'm calculating the second derivative of the function. So I'm first approximating it by the polynomial here, and then I'm using the chain rule, but twice. Okay, once for the first derivative, dp d alpha dx, and then d alpha times d alpha dx. So that gives me a 1 over h squared, because d alpha dx, as I said, is 1 over h. Because I have it twice, I'm going to have this. So I'm going to take the derivative of the polynomial twice. First with respect to alpha, again the result will be taken, again a derivative with respect to alpha. So I lose the first two terms of the polynomial expansion. The first term that survives is delta squared. And then I need to do a chain rule expansion for the next term. Okay? And that is the reason why none of these polynomials will give, the approximations will give you exactly 0, even when you evaluate them at alpha equal to 0 or 1 or 2. Okay? And the order of the error goes down by 2 for a second degree. Polynomials had an error of h to the power m for an mth degree polynomial, but this one will have m minus 2. And you can do the same trick. Now evaluate it at alpha equal to 0 or alpha equal to 1 or alpha equal to 2. Take 1 term, 2 term, 3 term, etc. And you'll get a whole class of formula. And this one is a second derivative approximation. It's a 3-point forward difference approximation. That's a terminology that people use, okay? Because it uses 3-point from the reference point, 3-point forward difference formula with a truncation error of order h. And if you do the 2-term expansion, you will get a 4-point forward difference formula. Okay, at the same reference location at x1. But if you put alpha equal to 1, you are calculating it at a different location. Okay, and once again you can do 2-point, 3-point, etc. But this one is an important one. It's a central difference approximation of order h squared for the second derivative at x2. Okay, the reference point. So f double prime at x2. So these two formula that I said as important one, the central difference for the first derivative and the central difference for the second derivative, they have the same truncation error of order h squared. So when you are approximating like you did in the Brad-2 problem, a differential equation, if it has the second derivative, first derivative, etc., you must make sure that each one is approximated by a term with the same order of truncation error, because the total error in the problem will be determined by the term that has the lowest truncation, the highest error. Okay, so you want to keep the error low. Am I making sense or not? Okay. So here is a table that summarizes some of the important formula that you will need. Okay, so the important ones here would be the central difference. Which one would be the central difference for first derivative? F of xi equals xi plus 1 minus xi minus 1. That would be important. And similarly, the central difference for the second derivative, which is what you used in your Brad-2 problem. Okay, the derivative of xi depends on xi minus 1, xi plus 1, and xi. Okay, they both have the same truncation error. The other formula that are equally important would be on problems where you have a derivative boundary condition. Okay, suppose I say the first derivative in the same problem that you did, I say df dx at x equal to a, that is the left boundary, is 0. Not the function, but the derivative. Okay, I don't know whether I asked you to do this. I think I asked the other class to do that. That is, the Brad-2 problem, you have the symmetry, right, in the solution. So you're solving from -1 to +1. I could say solve the same problem, but over 1/2 domain. Why? Because it's symmetric. Okay. What is the advantage? We can get the same accuracy instead of using 40 grid points, 20 grid points, because you only have the number of grid points. Right? You will have the same step size, so you will have the same truncation error for that. But what is the boundary condition at this point? The derivative has to be 0. Right? So what do you do when you have that? We will see when we actually develop finite difference methods. But you can, from this formula at this stage, if I say pick a formula that has the first derivative approximation for a first derivative with the same truncation error, but because it applies on the left-hand side, I need to use data points only ahead of it. I don't have any data points behind it, right? Which formula would you pick? The third one, right? The third one is the approximation for the first derivative. Now you will just put I equal to 0, the left boundary, and you will take minus 3 f0 plus 4 f1 minus f2 over 2h, because it has the same truncation error. So you need to match the truncation error in every approximation that you do in solving a problem, whether it is in the differential equations or the boundary conditions, because the total error will be governed by the one that has the most error. So you want to match it. That has problems too. We'll discuss what problems we will come across when we do that. Okay. Any questions? So the functional representation using Newton polynomials is extremely useful for this purpose in derivatives. Provides us tools for approximating derivatives and solving differential problems. That's what allows us to convert a differential equation into a set of algebraic equations using discrete data points. Okay. Do you have any questions?
Do you do the same thing for your initial point, since you don't have like a central difference on the first point that you use? So it's either marching forward through X. At first point, you have to use a through point.
Yeah. Are you talking about solving ordinary differential equations in time, marching ahead, or
Something like that. Right?
Yeah, that's exactly a place where we come across a problem. When we're developing approximations for solving what we call initial value problems, where the independent variable is time. So you have differential equation like the Lorentz equation or the Mueller-Eberhard paper that we saw, 3 ordinary differential equations. So you have an initial condition. Now only one data point, right? How do I predict the next one? Okay, and how do I increase the accuracy of the next prediction? So there are methods that will take 2 points, 3 points ahead. But the problem is these are all unknowns. So if you, in the very first step, if you use 2 points ahead, you have to solve 2 equations simultaneously. Okay, and all these methods avoid that. So you want to have only one unknown at the front part. So one trick that ODE45, ODE15S in Matlab would use is what is called variable order method. Okay, and these have been developed in the 50s and 60s, I think. So the idea is, in the very first step, I will take an extremely small step because I want to control the truncation error. Okay, but as I accumulate more points, so if I'm here and I'm going to go to predict the next one, it makes sense for me to use all the 3 data points behind. Okay, then I will increase the order of the method. So this is why it's called a variable order method. So increase the order of the method as you have more data points. Striking a balance, you don't go beyond 3rd order, 4th order, 5th order at the most. Right? So that, yeah, so we have to have ability to change the step size. That also introduces a whole new ball game. But if you guys have started thinking about it, then you can understand. What I want you to get out of this course is when you're using COMSOL or Fluent or any other package, an awareness of what algorithms they use, how do they manipulate or manage the errors, and how can I use that in an intelligent fashion. Last night, my son was showing me, this is a departure from the course, but I think it's a valuable lesson. He's in 10th grade. So he watches the TED Talks. I don't know whether you guys know about it. They are wonderful lectures. And there was one guy who was talking about the human-machine interaction. Okay. At one time, we thought the computers will rule the world. They will solve all the problems for us. When we had examples like computers being able to beat the chess master. Right? And the more recent understanding and experiments show that you can use computers in making your move in a chess game, okay? And then 2 people pitched against each other. They can use whatever computers they want to see who wins, right? And there were 3 kids who had 3 very minimal lousy computers. So they do the analysis on the computer to find the next move, but they are the ones who make the decision, right? Compared to another pair, that one person with a very powerful big computer. and these kids beat that person, right? So the idea is that computers can help us, but we need to be intelligent about making key design decisions, okay? Then what we can achieve is much bigger than let the computer make all these decisions for you, okay? So in building a mesh, for example, there are automatic mesh size adjustment programs, okay? So you say, okay, everything automatic, you make the decision for me, you are not necessarily going to get the best result. So you need to understand the underlying ideas so that you use it, because it has certain abilities for looking at millions of, in the chess case, for example, millions of moves, and suggest 3 or 4 that are good, okay? And then you make the decision finally which one you want to make. So it is an important lesson for me last night, that how human machine interaction can produce better results than just completely relying on computers. But without these computers, we cannot solve any of these problems, right? So we also have to recognize that. So digression, sorry for the digression. Now, this same formula that we derived, we're going to derive again from the Taylor series expansion. So it's a different approach, but we get something additional from this that will help us understand how to control the sources of errors, okay? So what we are doing here is just a Taylor series expansion of the function about some reference point xi in step size of h, okay? So the standard Taylor series expansion is, it is f of xi plus f prime times the step h plus f double prime times h square over 2 plus f triple prime, which will be h cube over 3, etc. Okay, so we are not using the polynomial representation yet, but we are going to effectively amounts to that, okay? Then you do the same expansion around the same point with minus h, okay? So I'm calculating the function at xi minus h, which is given by this expansion for the Taylor series. Now, if I'm interested in calculating the first derivative approximation, so I'm interested in this, what kind of arithmetic operations will keep that and try to cancel as many terms succeeding that, okay? For example, if I subtract it, I'm going to lose that term. But if I add them, sorry, if I add them, I'm going to lose that term. If I subtract them, I will have that term surviving, okay? So I'm going to subtract a minus b. So if I call this as a, and call this as b, excuse me, a minus b is going to give me fi plus 1 minus fi minus 1, because I'm subtracting it on the left hand side, equals, the fi will cancel out, and I will get 2 times h times f prime at I. Okay, but what about the next term? They will cancel out. What about the next term? That will be of order h cube. That is the error I need to sustain. Okay? So I get an approximation for the first derivative at reference point using point I minus 1 and I plus 1 divided by 2h. It is exactly the same formula that I derived before for central difference approximation for the first derivative. Okay? But it has the same truncation error of order h cube. So it looks like I haven't really gained much. I just derived the same formula through a different method. But what I would like you to focus is the form of the neglected term. What is the form of the neglected term? It has f triple prime evaluated at the reference point. Again, if I can estimate that, I'm doing well because I can add that, right? But I cannot estimate that because I don't know what the solution is. So I need to live with that. But it is a term, of course, I have to divide everything by h, or 2h here. Divide by 2h. Cancel that. And that will then become h squared. Okay, so I will have a term which is of order h squared. So I get to know how the grid size controls the error. It is of order h squared. But I also know that there is another term, a disruptive term, that can control the error. Okay, and that is the third derivative. Okay, so this tells me an insight that if I have a problem where the derivative is very sharp in certain regions and the derivative is very small in other regions. Okay, so even though I may be using a constant step size, what happens to the error in this region? would be small because the function doesn't change. So its derivatives should also be going to 0. Okay? But if I have a very sharp change in certain regions, even if I use delta H small, this could still be very large. So the error is composed of both parts. And that is why we need, when we talked about, Manunal talked about boundary layers, where there is a sharp gradient in a flow problem, you want to put more grid points. Why? Because you know in those regions this is going to be dominant. This derivative term is going to be dominant, so you're trying to control the error by putting more grid points. Whereas in regions where things don't change as fast, this term is going to be small, so you can take a larger step size. Why would you want to do that? Why don't you use small spacing everywhere? You want to manage the size of the problem, right? So if you use the small step size everywhere, you end up with a huge problem. So the trick is to manage the distribution of the truncation error in a problem where it's varying in space. It's not a difficult problem. It's not an easy problem to solve because you don't know the solution beforehand. So in two-dimensional situations, you might have one corner where there are sharp changes, in another region where there is not much of a change. And so you need to find out what the error distribution is. These are errors at a particular point. Okay, so every grid point will have an error. And so there is an error distribution, and the error distribution follows the same differential equation in patterns. Okay, but the derivative-based methods for adaptive gridding are more popular, and all they do is they estimate the derivatives, and if the derivative is sharp in one region, they'll put more points. Okay. So human-machine interaction is very important. In getting good numerical results, grid distribution is very important. Okay. Any questions on that? Okay, so that is the central difference approximation for the first derivative, and you go through the same step, adding the two equations instead of subtracting them. So then you get fi plus 1 plus fi minus 1 equals 2fi, because the first two terms add up, but the first derivative cancels out. You are lucky the first derivative cancels out if you add them. So the next term would be the second derivative which survives, and this will cancel out, and the next term would be the fourth derivative. Okay, and so you can get an expression for the second derivative approximation, and that gives you the second most important formula. These are the two central difference formula for first derivative and second derivative. They both have the same truncation error. We derived both of them from the polynomial, but we actually get a better sense of what the truncation error looks like. Okay, what is that? The fourth derivative of the function has a role in determining what the truncation error is. So that's going to form the basis for numerical numerical method, finite difference method for solving differential equations, and also for developing multi-step methods for ordinary differential equations, which we'll get to very soon. Numerical integration. I'm not going to spend a lot of time on this, just to show you that the same formula can be used. The Newton forward formula and the Newton backward formula can be used to solve this problem. The problem is find out what the integral of a certain function is between two limits a and b. Okay. And geometrically, the problem basically amounts to this. You have a function, you are given the function, there is no analytical integration for that. In those situations you can use that. What you need to do is evaluate the function at a number of discrete points. So construct the table. Okay. If you are given the function, construct the table. Or if you are not given the function, you are given a tabular data directly that is coming from an experiment, but you need to evaluate the integral, you can still use the same ideas. And so the first thing that you do is fit a polynomial of a certain degree and then integrate the polynomial. Okay. So if you integrate the polynomial truncated after different series, you get a different type of integration formula. The simplest one is the trapezoidal rule, right? You're all familiar with that. So in a trapezoidal rule, all you do is you take 2 points and treat this as a trapezoid. So this is a linear approximation between those 2 points. Okay? Just like in the first derivative, we put a linear approximation and take the derivative. We put a linear approximation and find the area under that. That will be, according to the trapezoid, the area of that trapezoid will be half the height f1 and f2 multiplied by h. Okay, and you just repeat that because it's an integral, it's a summation. So then you find the strip, the next strip, and the next strip, and then add them all up to get the total integral. So Matlab has a function called trapeze, what is it called? T-R-A-P, right? And it'll take a set of data points and apply this formula to give you an estimate of the integral. But what I wanted to show is what is the truncation error. Okay, that's purely a geometrical interpretation, and from that I can derive the formula. But if you use this approach, you get an idea of what the truncation error is. Okay, so once again, h is b minus a over n. A to b is a range, so you divide that into n equal intervals to find out what the step size is. And then this is the coordinate transformation from x to alpha. Okay, so you have f of x, and you're going to do only from x0 to x1, one of the first strips in that integral. Okay, so when you make this coordinate transformation, what happens when x equal to x0, the lower limit, alpha is 0. And what happens when x equal to x1? Alpha is 1. Okay, so the limit changes to 0 to 1, and the polynomial approximation is replacing the function. It's a first degree polynomial, okay, p1 at x0 plus alpha h. But what happens to dx in the formula? Dx is h times d alpha, right? So you need to make the coordinate transformation. So you have an h times d alpha. So instead of dividing by h, you have a multiplication by h. So you get more accurate results in integration. That's the reason why that happens. So the neglected term is going to have an error because it's a linear polynomial approximation. The next term in the neglected series would be of order h squared, but that gets multiplied by h. Okay, it's a term that we are not going to be evaluating. So we're just trying to keep track of what this error is. So the error is going to be of order h cubed. Okay, and you replace this by 1 plus alpha delta f0 h d alpha. Carry out the integration with respect to alpha. Okay, so you have h as a constant that comes out, and then integral of f0 is alpha times f0. Integral of delta f0, but alpha. We have alpha d alpha. It's going to be alpha squared over 2. Substitute the limits, and you get the trapezoidal rule. But you also get the information that it is going to be of order h cubed per step. Okay, this is going from x0 to x1. But what is this is called a local truncation error. Okay, so this is the local. I think it's not, doesn't want to cooperate. Local truncation error. Okay, truncation error. But you are going to add all of these different pieces of integration that I showed you in the figure before. So this is for the blue part, one integration going from x0 to x1. Then I need to go from x1 to x2, x2 to x3, the same formula, I'm going to sum it up. So that is called a global truncation error because the error in every step is added together. Okay. So what will the global truncation error be? Well, now we are going from A to B. Okay, but we are splitting this as summation of n strips. Okay, each one with this formula h over 2 fi plus 1, fi minus 1 plus fi. So this is the local error, but because we are doing it n times for each one of those strips, and n is b minus a over h, if you assume that this is of the same order for every strip, this summation can be replaced by a product, right? Because I'm doing it n times. So substitute for n, which will be b minus a over h. So I get a 1 over h here from that. That lowers the truncation error. So the global truncation error will always be one order lower than the local truncation error. And this idea also applies to integrating ordinary differential equations. You'll find integrating ordinary differential equations, initial value problems, borrow a lot of ideas from this type of an integration method. And Simpson's rule is essentially the same idea for the next term. So instead of first degree polynomial, you take the second degree polynomial. Okay, but there is something surprising happens here, and that is the next neglected term in the series spontaneously happens to be 0, just sheer coincidence or luck. Okay, so that's why the Simpson's method is actually more accurate than what you should expect for a second degree polynomial. And that is the reason why I think I have kind of shown you what would happen. So now we are going to integrate, we are going to put a second degree polynomial through these three data points, 1, 2, and 3. A second degree polynomial, which is what we are doing here, and integrating from x0 to x2. So we are taking this as one strip and then repeating that. Okay, so it goes from x0 to x2, and that makes the limit go from 0 to 2. And you plug in the second degree polynomial and keep track of the next neglected term, and also carry out the integration. Okay, and you will find that turns out to be 0. So really the next neglected term is the truncation error for Simpson's method. And Simpson's method has a local truncation error. See, this term turns out to be 0 and has a local truncation error of about h to the power 5. And the formula turns out to be h over 3 f0 plus 4 f1 plus f2. So it takes 3 data points, puts a quadratic, and gives you an expression that is the area under those those 3 data points. And you need to apply that repeatedly. Okay? And when you repeatedly apply it from A to B, the global truncation error will go down by 1. It becomes of order h to the power 4. So Matlab has a number of functions. Oh, we're almost out of time. Okay. So there is symbolic toolbox in Matlab. So if I define a variable as a symbol using the command syms, then it's just an example. So if I have this function e to the power minus x sine 2x minus 2, I can integrate that analytically. There is a function called int, okay, and it takes that symbolic expression. Now f automatically becomes a symbolic expression because it is based on x. So x doesn't have any numbers at this stage, okay, and so if you pass that function f and between the limits 0 to 2, it will actually carry out the integration and substitute the limits for 2 and 0, and this is the answer. Because it is doing symbolically, it actually integrates it and plugs in the numbers. If it cannot integrate it analytically, then it will switch automatically to the numerical one. And here I'm just extracting the answer to 4 precisions. Because this is exact, you can extract the result to any number of precisions. And there is another called VPA, Variable Precision Arithmetic. Using that, you can get answers to more than 20 decimal places if you want. That's part of the symbolic processing toolbox. So the exact answer to 4 decimal places is 0.3504. But if you want to do it numerically, then you need to write the same function, but as a numerical one. So this is a function that I write in Matlab. I pass a value of x, it gives me a value of f. So it's a numerical evaluation. And then I create a vector x going from 0 to 2 in steps of 0.1. And I plot the function. That's how the function looks. Okay? And there is a function called quad, but trapeze, I guess. Yeah, I told you about trapeze, TRAPZ. That uses trapezoidal rule, but there is also a function called quad, which gives you more accurate results. Like you will see, trapeze has already minus 0.3579. The exact one is minus 0.3504. Okay, so to improve the accuracy of it, here I used a step size of 0.5. That has only 2 significant digits. Why? The truncation error is large. If I use a step size of 0.01, evaluate the functions at more points and controlling the error. So I'm going to get the same result as I got analytically, 0.3504. But if I use the quad function, and this is something I would encourage you to play with, pass the function and give the same limit, it will also give you very accurate result to 16 significant digits. We can control the error. We can control the truncation error. That's one of the arguments in there. It gives you the same result. What does quad do that trapeze doesn't do? It uses adaptive quadrature. So it will initially put 4 points between the limit 0 and 2, get an error, get an integral. Then it will put 8 points, get an integral. It will compare these 2 integrals. If it is more than the tolerance that you have specified, it's going to put 16. It's going to put 32. Okay? So it continuously refines a number of grid points until it meets the tolerance that you have provided. That is, the 2 results are not differing more than the tolerance that you have specified. This is the kind of thing that you need to do in your project for grid independence test. At least get the result in 2 different grid sizes and see some integral measure of the solution remains small. Okay, that's the idea of a grid independence. Yeah.
Where did you specify the tolerance for this?
It has, like most programs, it has a built-in tolerance, which is 10 to the minus 7 or something like that. But there is a parameter next that you can specify through options. That is the standardization that Matlab is doing now. So there is an option structure which has a number of things that are related to that algorithm that you can specify. And there will be a variable called RELTOL, relative tolerance, or ABSTOL or something like that.
A follow-up question on the trapezoidal rule.
Yeah.
Sorry, on your solution, you said it was converging to a value that's very close to the true value, I guess, the analytical solution. If we were to take out more decimal places,
Yeah.
would it just be like, I mean, then it would start deviating after probably 4, right? Because that's the order of magnitude of the ChE. Am I understanding that correctly?
That's a good question. So if I have coarse grid and my truncation error is limited to h square, okay, in trapezoidal rule, okay, so will I get further agreement between the trapezoidal rule and the exact answer that the analytical one gave? The answer is that you will be stuck. So if you're using a step size of 0.01, you will get 0.0001, and after that your result will never agree with that, no matter how many grid points you put, right? Sorry, you can't control that by controlling the step size. If you take more grid points, you can control it, so you can get more and more accuracy.
I just wanted to make sure that I was understanding the fact that if you use the trapezoidal rule and then enumerate out all the decimals, essentially that at some point you would start disagreeing again, and it would be at the old mag page, or the mag page.
Yeah, of the order, the global error will be of order h squared for the trapezoidal rule, but even if you indefinitely decrease the step size, you cannot get indefinitely increasing precision. Unlike in the analytical method, okay? In the analytical method, you can get any precision you want. You can put, instead of 428, you will get this result for 128 significant digits. They will all be accurate, okay? Because it is doing it in symbolic processing toolbox. And in numerical, you will be limited to 16 digits because the number representation allows you only 16-digit accuracy. So even if you go for 10 to the minus 16 grid size and say, can I get 10 to the minus 16 times 2 as my error, you cannot get that because of the numerical representation. Yeah. Okay, I think we have exceeded the time. Any questions? So in the next class, what I'm going to do is look at other functional approximations using basic polynomial, Chebyshev polynomial, and we will introduce the idea of orthogonal polynomials and look at how we can use that as a basis functions. We've seen the regular polynomials 1x squared as a basis function. You've seen Newton polynomial approximations. Next we'll move to that, and once we finish that, we can start looking at ordinary differential equations. Okay, we'll stop there.